Okay, perhaps we can begin, and we are also live on YouTube, so some people will also join via YouTube. So, welcome everybody to this week's Majorana-Raychaudhuri seminar series. Our first speaker for today is Dr. Anne Green from University of Nottingham, and she is going to speak about primordial black holes as dark matter candidate. So, maybe I'll just send you a reminder when 5 minutes are left.
Okay, thank you. Yes, so I'm going to start by giving a very brief introduction to the motivation and history of primordial black holes as a dark matter candidate. I'm then going to talk about their formation, current status of observational constraints or signatures of primordial black holes, and then if time permits, finish very briefly talking about what I think are the key open questions in the field. And at the bottom, I've referenced two review papers, one which I wrote with Bradley Kavanagh and the other which Bernard Carr and Florian Kuhnel wrote. So if you'd like to know more about the motivation and history, there's a textbook, Primordial Black Holes, which is due to be published very shortly by Springer. And the opening chapter of that by Bernard Carr and myself is on the history. So that goes into a lot more detail, in particular from Bernard's expert perspective on the history. So primordial black holes are different from astrophysical black holes in that they are black holes that can form from overdensities in the early universe. And I'll talk a bit more about that in a moment. And as they form before nucleosynthesis, and indeed actually before the quark-hadron phase transition, that means that they are non-baryonic, which is one of the key requirements for a good dark matter candidate. They famously evaporate, we believe, by emitting Hawking radiation. And in the standard picture, the lifetime of a primordial of any black hole is longer than the age of the universe if its mass is greater than about 10 to the 15 grams, which is roughly the mass of a mountain for context. They are very different from most dark matter candidates, the ones that are typically considered like WIMPs, axions, and sterile neutrinos, in that they're not a new particle. Sometimes people say that means they have the advantage that they don't require beyond the standard model physics. However, I think that that's probably not quite true. Generating the large overdensities you need to form them typically does require some sort of beyond the standard model physics, for instance, inflation. So it was realised that primordial black holes are a viable cold dark matter candidate in the 1970s. One of the very early papers by Stephen Hawking mentioned that. And there was a first wave of interest in the possibility that solar mass primordial black holes could be the dark matter in the late 1990s. And that was due to an excess of microlensing events seen towards the LMC that would be being produced by roughly solar mass objects. There were too many of them for them to be stars or stellar remnants due to Big Bang nucleosynthesis arguments. And so the suggestion was that they could be primordial black holes. However, with future surveys, that excess wasn't confirmed, and so the sort of interest sort of faded a bit. At that time, though, there was a paper written by Nakamura et al., and they pointed out that if a significant fraction of the dark matter was in the form of primordial black holes, then primordial black hole binaries would form in the early universe. And if those binaries survived to the present day without their orbits being distorted too much, then gravitational waves from their coalescence would be detectable by LIGO. Most people, myself included, more or less forgot about that paper. However, as we all know, sort of getting on for a decade ago, LIGO Virgo did indeed detect gravitational waves from mergers of massive tens of solar mass black holes. My understanding is that the current consensus is that most, and quite possibly all, of those black holes are astrophysical black holes. Although at the time of the announcement, this was perhaps quite surprising, and that people perhaps didn't expect there to be quite as many astrophysical black holes formed to generate this large number of merger events. And hence there was a couple of papers which came out soon after the announcement arguing that, could some or all of those black holes be primordial and also a significant component of the dark matter. And this, if you look on Inspire at the number of papers that have been published on primordial black holes, has generated a huge rise, which is maybe just about beginning to plateau off now. So to form a primordial black hole, you need an overdensity so large that it sort of collapses to within its own Schwarzschild radius. And the most commonly studied mechanism, and arguably the most minimal, is the collapse of large density perturbations, which would be generated during inflation and then would collapse later on during radiation domination. And these are the same density perturbations from which structures form, galaxies and galaxy clusters, but on much shorter length scales. And as we'll see in a moment, they have to have much higher amplitude. And so simply what's happening here is that if a region is sufficiently overdense, then shortly after it enters the horizon, i.e. becomes comparable in size to the observable universe, gravity overcomes pressure and it collapses to form a black hole. Although there are various other mechanisms via processes in the early universe which can generate large overdensities that can form primordial black holes, and I've listed some of the ones that are most historically popular on the slide. So what we'll do now is have a quick look at the requirements for a density perturbation to form a primordial black hole. This zeroth order analysis goes back to Bernard Carr. If you want to do concrete calculations, you have to do better than this, but it actually captures the key physics really very well. So in simple terms, you can state the threshold for primordial black hole formation in terms of the density contrast, the size of the density of a particular region relative to the background density at the time that region enters the horizon. And for a primordial black hole to form, it has to be greater than some critical threshold value, which is of order the equation of state parameter W, which during radiation domination is roughly 1/3. And if that criteria is satisfied, then you get a black hole formed with its mass being roughly equal to the horizon mass. And that it depends on time, it grows with time. And so the lightest black holes that wouldn't have evaporated by the present day, the 10 to the 15 gram ones, they would have formed 10 to the minus 23 seconds after the Big Bang, whereas solar mass ones would form around the time of the QCD phase transition. And we'll see why that's interesting in a moment. However, in recent years, there's been a lot of work in refining the criteria for PBH formation, and the threshold actually depends on the shape of the perturbation and is best specified in terms of something called the compaction function. So that's the sort of thing you need to look into if you want to do concrete calculations. Next thing we want to do is calculate how many primordial black holes we form. This is typically parameterized in terms of something called beta, the initial primordial black hole mass fraction, which is the fraction of the universe in regions that are dense enough to form primordial black holes at the time they form. So you take the probability distribution of your density contrast, smoothed on a particular scale, which we're specifying here in terms of the horizon mass, i.e. the mass of the primordial black hole that forms roughly, and then you integrate that distribution from the threshold up to infinity. If you assume a Gaussian probability distribution, and I'll come back to that assumption later, what you then get for beta is a complementary error function, which depends on the threshold, and then also this quantity sigma, which is the mass variance or typical size of the fluctuations. And so this picture shows a roughly Gaussian probability distribution with width equal to the mass variance. And the primordial black holes are forming from these rare large fluctuations out in the tail of the distribution. As we will see very shortly, in fact, beta, the initial fraction, has to be very small. So that's telling us that sigma, the width, has to be much less than delta C. So in reality, that distribution would be very narrow. And in this case, our complementary error function can be written in terms of this exponential. And so you see that you actually have to have fine tuning of the mass variance to get, a particular abundance of primordial black holes. We now want to link the initial abundance of primordial black holes to their abundance today. And a key thing here is that because they're matter and they form during radiation domination, for a long period of time, the fraction of the energy density that's in the form of primordial black holes grows. Their energy density is diluting as the scale factor cubed, whereas radiation goes as A to the 4, so the ratio grows proportional to A. So what we see is the fraction of the total energy in the form of primordial black holes grows up to matter radiation equality and then becomes constant during matter domination. And if you track back from a particular fraction of the dark matter being in the form of primordial black holes today, you can work out what your initial abundance has to be. And what you get roughly is this expression here. So we see that if you want all of the dark matter to be in the form of solar mass primordial black holes, then the initial abundance has to be 10 to the minus 9, i.e. very small. And the lighter primordial black holes would form earlier, so their initial abundance would be even smaller. On CMB scales, cosmic microwave background, we've measured the amplitude of the primordial perturbations very accurately, and that amplitude is of order 10 to the minus 5. And so we can already see that if the primordial perturbations are very close to scale invariant, i.e. have roughly the same amplitude on all scales, then the number of primordial black holes will form will be completely negligible. So we can take our expression in terms of the complementary error function in, put a threshold a bit less than unity, sigma of order 10 to the minus 5, and what you get is completely tiny. You can invert this argument and work out how big sigma has to be to the typical size of the fluctuations to get an interesting abundance of primordial black holes. And to me, an interesting abundance means a non-negligible fraction of the dark matter today. And the answer is the square of the mass variance, which is roughly equal to the primordial power spectrum of the primordial curvature perturbation, is of order 0.01. So you have to grow the fluctuations by many orders, several orders of magnitude relative to their value on cosmological scales. And so this is shown in this plot here in sigma squared as a function of co-moving wave number k, or alternatively the horizon mass, which is roughly equal to the PBH mass. So on cosmological scales, we have accurate measurements of the perturbations. There's a small gap between these excluded regions. And this line then is roughly the amplitude required for all of the dark matter to be primordial black holes. There are also some constraints on the amplitude of the primordial power spectrum. Large density perturbations on slightly smaller physical scales than probed by Planck and the Lyman alpha forest can cause CMB spectral distortions. And we've got this green excluded region from FIRAS, which was on COBE. And these constraints could potentially be tightened by sort of proposed future experiments like the PIXI. Also, large density perturbations would lead to large tensor perturbations in the form of scalar-induced gravitational waves, and they can be constrained. Well, currently it's been done using pulsar timing arrays, and in the future it could be done by SKA and LISA. And so at the moment, these constraints on the primordial power spectrum aren't ruling out primordial black holes forming from large density perturbations, but they're beginning to constrain the scenario and sort of could put it under severe pressure in the future. There are a few important deviations from the simple scenario I've talked about that I'd like to mention. So the first one is critical collapse. It's a general phenomenon in gravitational collapse, and Niemeyer and Jadamczyk in the late 90s pointed out it would apply to primordial black hole formation. And in this case, the mass of a black hole formed depends on the size of the fluctuation it forms from. So how big the fluctuation is relative to the threshold value. And so the masses are still typically of order the horizon mass, but you do get this spread of masses. And so this is important, that even if all of the primordial black holes form at the same time, you do get some spread in the masses. So we don't expect the mass function to be a delta function. Another important thing is the effect of phase transitions. If you have a reduction in pressure, this means the threshold for collapse gets smaller, And hence, for a fixed value of the amplitude of the perturbations, you increase the abundance. And this is particularly interesting because the QCD phase transition occurs when the horizon mass is roughly a solar mass. So if your perturbations have roughly the same amplitude across a range of scales, then you expect enhanced formation around a solar mass and also around other scales corresponding to other phase transitions. But the key thing to emphasize here, though, is that you still do need large fluctuations. It's a relatively small decrease in the sort of threshold for collapse. And then the other really important thing is non-Gaussianity. So we've already seen that the primordial black holes are being formed from rare, large density fluctuations in the tail of the probability distribution. So changes in that shape can significantly affect the PBH abundance. And this was sort of realized this was important way back in the 1990s. Another crucial thing that's been realized more recently is that because the relationship between density and curvature perturbations is nonlinear, large density perturbations are inevitably non-Gaussian. So even if the curvature perturbations were Gaussian, the density perturbations wouldn't be. So we now need to have a think about what we need to do to form large PBH forming density perturbations, and inflation is commonly thought to be the mechanism via which density perturbations are generated. I'll start with a very brief crash course stroke reminder about what inflation is. So it's a period of accelerated expansion proposed to have occurred in the very early universe in order to solve various problems with the Big Bang, namely the flatness, horizon, and monopole problems. It's usually driven by a slowly rolling scalar field, and that scalar field, as well as causing accelerated expansion, it has quantum fluctuations that then generate density perturbations. And the scale dependence of those primordial perturbations depends on the shape of the potential. And so here we've got a sort of cartoon of a sort of inflation potential. We've got our field, slow rolls down here, up until the point the potential gets too steep to support inflation, and then inflation ends, the field decays, and the universe reheats. And in the slow roll approximation, the mass variance squared, i.e. the square of the typical size of the perturbations, is related to the potential and its slope by this expression here. And so the scales that are probed by large-scale structure in the CMB correspond to a relatively narrow region of the potential, whereas large PBH forming fluctuations could, in principle, form across a much wider range of the potential. So what do we need to do to produce large perturbations? So we previously saw in the slow roll approximation this expression here for the typical size. And so you can see that if we want sigma to be large, one way of doing this is to make V prime, the slope of the potential, very sort of small. And it was realized again in the 1990s that if you have a plateau in your potential, you can generate large perturbations, which form an interesting number of PBHs. Although a caution here is that in the ultra slow roll limit, as in when the slope tends to zero, the slow roll approximation actually isn't valid. And so you need to do a numerical calculation of the perturbations. And as I'll mention briefly at the end, if I've got time, ultra slow roll also affects the probability distribution of the fluctuations. So we have three key requirements for a PBH producing inflation model. The first thing it has to do is produce the measured power spectrum, both its amplitude and scale dependence on cosmological scales. We then need the amplitude of perturbations to be 3 or 4 orders of magnitude larger on some smaller scale. And then finally, inflation has to end. And it turns out it's hard to satisfy all three of those requirements in single field models. Essentially, you need fine-tuning of the potential. And so on the sort of left, we've got an example of what we need to do. We've got this region in green here that's matching the CMB and large-scale structure observations. And then into the potential is inserted a tiny little bump that you can sort of zoom in and see. And what's happening is you have to slow the field down, but not so that it comes to a complete stop. So the sort of field slows it down and then just makes it over the bump, and then the potential steepens and inflation ends. And if you do that for this sort of model with the fine-tuned potential on the left, This is the primordial power spectrum you get in red. So this is the same plot as we saw before. The black line is roughly what you need for all of the dark matter to be primordial black holes. And so, you can do it. And it's been shown sort of that quite generally, if you don't fine tune things, the steepest growth you can get is roughly k to the 4. And I guess the other thing to note here, the red line is an accurate numerical calculation, whereas the blue line is what you would get if you did it analytically, showing that, if you want to get it right, you need to do it numerically. So you can do it in single field inflation, but it's fine tuned. There are many, many inflation models, though, and if you go to, for instance, multiple field models, it maybe becomes a bit easier because you can have different fields satisfying different ones of the requirements that we need to satisfy. And so, for instance, a model that's been popular going back to the 1990s is hybrid inflation, and the particular case of what's called a mild waterfall transition. So in hybrid inflation, the potential looks like the left. Initially, the field rolls down this local minimum, but eventually we get to a point where actually that's no longer the minimum. We've got these two global minimum, and the field transfers to one of them. And if this transition happens neither too fast nor too slow, you can get a broad peak in the power spectrum, which reaches the required amplitude to produce an interesting number of primordial black holes. There are various other possibilities. The thing to bear in mind here is there are many hundreds of inflation models, and there are some subset of them, and I've listed sort of some of the things people have talked about, which can produce large primordial black hole forming perturbations, but it's not a generic feature of inflation. And if you're interested in this, then there's a couple of review papers I've mentioned here. So we can form interesting abundance of primordial black holes. Whether or not that is actually what's happened in the universe, that's a question that has to be answered using observations. And so what I'm showing you here is a compilation of the tightest observational constraints. Now, obviously, going from data to constraints always involves assumptions, and there are various sort of standard assumptions that are made here about the distribution of the primordial black holes, and in particular clustering, and I'll talk about those later on if I have time. The key one is that all of the primordial black holes have the same mass, they're all of a single mass, and I will talk in a moment about how that affects the constraints. There are many, many different constraints, and it would take far longer than I've got to talk through all of them. So instead, I'm showing you this compilation. So if we go down to the lightest primordial black holes that won't have completed their evaporation by the present day, so we're talking from about 10 to the 15 grams up, those black holes will have started evaporating, and hence there are constraints on their abundance from the products of their evaporation, for instance, high energy gamma rays. Microlensing is a very powerful way of constraining stellar and planetary mass primordial black holes. And this is a temporary brightening of a particular object. It's sort of strong lensing where you get multiple images, but the separation of those images is micro arc seconds, so it's too small to be resolved. So instead of seeing multiple images, you just see something get bright and then dim down again. And so here we've got sort of constraints that have reached of order the percent level on the abundance of primordial black holes. There are also constraints actually from gravitational waves, and it was realised in the months after the LIGO-Virgo announcement that probably if all of the dark matter was primordial black holes, then they would be merging at a rate so that you got several orders of magnitude more merger events than LIGO actually observed. So again, we're getting percent level constraints on the abundance of multisolar mass primordial black holes. And then going to even more massive primordial black holes, there are constraints from accretion. Gas would be accreted onto primordial black holes, and then that leads to emission. And it can show up either as X-ray and radio point sources at the present day, or via the effects on the recombination history of the universe, which show up in the cosmic microwave background. And then also, if you had the dark matter being made of very massive black holes or other compact objects, they would have all sorts of dynamical effects on the stars we can see. Wide binary stars would be disrupted, and the stars within dwarf galaxies would be heated. So once you get to very massive primordial black holes, there are tight limits. So summing up the key things from this plot, the multi-solar mass primordial black holes that everybody got excited about after LIGO Virgo, it appears that they're excluded unless there's something going very wrong with the calculation of multiple constraints. They can make up maybe 1% of the dark matter, but it really looks like they can't make up all of it. However, there is this open window, the asteroid mass window, since the masses of the primordial black holes are roughly equal to the mass of asteroids, where at the moment at least the primordial black holes could make up all of the dark matter. And this largely reflects the fact that asteroid mass compact objects are hard to detect. And at the very end, I'll come back to some ideas for doing that. So I told you earlier, though, that we shouldn't expect all of the primordial black holes to have the same mass. We expect by a critical collapse them to have a spread of masses. So an important question is, how does that affect these constraints? And what essentially happens is the constraints are smeared out. And so the tightest point becomes weaker, but you're excluding F of 1, i.e. all of the dark matter being primordial black holes over a wider range of masses. So these plots from a paper from Carr et al. This is a little bit old, so the constraints are not the up-to-date version I showed you on the previous slide, but the plots make the point nicely. So here on the left is what we have for a delta function mass function if all of the primordial black holes have a single mass. On the right, we've got what you get for a log normal mass function, which is a reasonable approximation to what we might expect from the various inflation models, taking into account critical collapse as a function of the central mass. And so if we, for instance, look at this HSC microlensing constraint, you can see the tightest value has got a bit weaker, but the range of masses for which F equals 1 is excluded has got bigger. And so still in this case on the right, we've got this small sort of slither of parameter space that's still allowed. And really what's important if you want to know whether this asteroid mass window is allowed or not is the shape of the tails of the mass function. This gamma rays, this will be from the high mass tail, the few of them that could be evaporating, and then this would be from the low mass tail over here. So it's the shapes of those things that depend how much these constraints close in. So I've talked largely about observational constraints, as in things we should be seeing if all of the dark matter was primordial black holes, but aren't seeing. There are people who take what they term to be a more positive perspective, i.e. they're looking at things we do see that could be due to primordial black holes. And if you're interested in that, then I strongly recommend this paper by Bernard Carr and his collaborators. And they go through a long list of observations that could potentially be explained by primordial black holes. Although that, of course, doesn't mean that there aren't other phenomena that could also explain these observations. So key open questions. Well, the obvious one from an observational point of view is how to probe asteroid mass primordial black holes. And people have had some ideas. And so I'll first go to the part at the bottom to try and explain why we need new ideas. There will be future better MEV gamma ray sort of satellites, and could they help? And the answer is only a little bit. And that's because the evaporation rate of primordial black holes drops off very rapidly with increasing mass. You might also wonder whether better microlensing observations could help. And the answer is, again, only a little bit. And the problem here is that once you get to 10 to the 22 grams, the primordial black holes are so small that the Schwarzschild radius is comparable to the wavelength of light. And this means that the normal geometric optics calculations of microlensing don't hold. You instead get wave effects, and that reduces the amplification, and hence, you don't get microlensing happening. And so you could, if you were clever and use sort of shortest possible wavelengths, get tighter constraints down to 10 to the 22 grams, but it would be hard to push down to lower masses. So new ideas are needed. And some of those new ideas have actually sort of been on the table for sort of several decades. For instance, you could look at femtolensing of gamma ray bursts, and so that then gives you interference fringes in this is what you're seeing. But again, there are problems with wave optics effects, and you would need very small gamma ray bursts to do that. Another possibility is what's called lensing parallax, where you're looking at a gamma ray burst from two different satellites at different points of their orbit, such that one is lensed and the other isn't. Microlensing of X-ray pulsars, that would be another way of getting around the wavelength issues. And then a sort of area that there's been a lot of more recent interest in is the effects on primordial black holes on stars, in particular in ultra-faint dwarf galaxies. And then also people have been looking at their effects on the orbits of planets in the solar system. And those later two ideas haven't yet made it into this plot, which I should have mentioned earlier, that I made using Bradley Kavanagh's PBH bounds code. And if I actually sort of go back to the slide, it's available on GitHub, so you can go there, you can make your own plots, you can choose what you're showing and how you're showing it. So there are some ideas, there'll be difficulties working out details, but we do have ideas for probing asteroid mass primordial black holes. A key question from the theoretical side of things, as in doing accurate calculations of the number of primordial black holes you produce for a given inflation model and what their mass distribution is, we need a much better understanding of the probability distribution of density perturbations, in particular produced by ultra-slow roll, which, as we saw before, is what's needed in single field inflation models to produce large PBH forming perturbations. And the issue here is that once something's rolling very slowly, stochastic effects are important. So the field getting kicked around and potentially back up the potential. And in some cases, at least, this can mean that the probability distribution has an exponential tail rather than a Gaussian one, i.e. you'd be getting more large perturbations. However, doing a complete calculation for a really concrete model, that's a big problem that a lot of people are working on, including Swagat Mishra, Ed Copeland and myself at Nottingham. So this is something where I think hard work from lots of people is needed to solve this one. Then another open question on the more astrophysical end of things is clustering, and in particular, how the primordial black hole distribution on galactic scales and smaller differs from that of particle dark matter. And this is something that could be extremely important. It would very definitely affect the rate at which primordial black hole binaries are merging, because obviously if dark matter is more clustered, that's going to affect their formation at late times, and then also their disruption, as in they could be sort of disrupting each other. And so it was sort of shown quite some time ago that if primordial black holes make up a large fraction of the dark matter, then you get clusters forming shortly after matter radiation equality. So really at relatively early times for structure formation. And the reason for this is that because primordial black holes are discrete objects, there will be Poisson fluctuations in their distribution, and hence, there would be clusters forming just where you happen to get more primordial black holes. How those PBH clusters evolve up to the present day, and in particular how the binaries within them evolve and how this affects the merger rate, that's a very difficult open problem. Here on the right, I've got a picture by Derek Inman and Yassine Ali Hamoud, where they did some really nice simulations of structure formation with both just primordial black holes and a mixture of primordial black holes and dark matter. And this is the end of their simulations at a redshift of around 100. And what you're seeing is you do indeed get lots of early clustering. But the problem is you technically you can't run a simulation with the dynamical range to resolve those structures up to the present day once they've merged within bigger structures. So this is a difficult problem. Nonetheless, it's possible to sort of try and think about the effects clustering would have on constraints. And one that in particular I've looked at along with various other people is how it would affect the microlensing constraints that are the tightest constraints across the subplanetary and stellar mass region. And it turns out that clusters formed from the collapse of Gaussian distributions are really quite sort of extended, so that the PBHs within them still act as microlenses individually rather than the cluster as a whole acting as a lens. And in this case, the change in the microlensing constraints is small. The obvious question here, though, is, well, we think that the perturbations are non-Gaussian, so what would happen in that case? And again, that's an open problem that needs working on. And so people have sort of tried to sort of make arguments generically, and in general, while the microlensing constraints would be weakened if you had relatively compact clusters, some of the other constraints, for instance, the ones from gravitational waves, the dynamical ones, and also constraints from the Lyman alpha forest, they would become tighter. So clustering isn't a panacea. It doesn't make the constraints magically melt away. Some would become weaker, others would become tighter. And so it's not that you can say, oh, clustering means that solar mass primordial black holes can be the dark matter. Maybe it does, maybe it doesn't, but you need to do concrete calculations. So to summarize, which will hopefully leave time for questions, primordial black holes are black holes that can form in the early universe, for instance, from the collapse of large density perturbations during radiation domination. However, to produce an interesting number of primordial black holes, by which I mean a non-negligible fraction of the dark matter today, then the amplitude of those perturbations must be roughly 3 orders of magnitude larger on small scales than the measured value on cosmological scales. This can be achieved in inflation models, for instance, with a feature in the potential or with multiple fields. However, it's not a natural or generic feature of inflation. On the observational side of things, there are numerous constraints on the abundance of primordial black holes, from gravitational lensing, their evaporation, dynamical effects, accretion, and other astrophysical processes. It appears that solar mass primordial black holes can't make up all of the dark matter, but lighter asteroid mass ones between about 10 to the 17 and 10 to the 22 grams could. The limits are collectively tighter for extended mass functions, which are what we expect, than they are for the delta functions that are assumed when calculating constraints usually. So an accurate calculation of the primordial black hole mass function is important for ascertaining whether that asteroid window really is open. Clustering is important. We know it's going to happen to some extent, and it will weaken some constraints and tighten others. So in my opinion, the key open questions in the field are how to probe light primordial black holes, accurate calculation of perturbations from ultra-slow roll inflation, and then hence accurate calculations of the mass function, and then also the clustering, how much of it we have at the present day and how it affects constraints. So that's it. Thank you.
Thanks, Professor Green, for this nice talk. So the participants, if you have any questions, you can please unmute and ask. Okay, so there are some questions in the chat box. So Adila Afzal is asking, people talk about memory burden effect. How seriously this should be taken?
Sorry, I couldn't hear the words in the middle of that sentence.
People talk about memory burden effect.
Oh.
How seriously this should be taken?
Okay, so the question is about memory burden. So for people who are not aware, this is a recent argument that actually primordial black hole formation won't complete, i.e. it won't continue until you're left with nothing or a Planck mass remnant, that it will actually sort of slow down at some point when the mass is equal to maybe half its initial mass. And then that would obviously significantly change the constraints on light primordial black holes, that it wouldn't be that everything below 10 to the 15 grams had evaporated away. You could have lighter ones still today being the dark matter. And the honest answer to that question is I don't know how much that should be taken seriously. It requires sort of expertise in the sort of detailed quantum mechanics of primordial black hole evaporation. That's not expertise I have, and unfortunately these days I'm too busy to have the time to put aside several weeks to really get to grips with that field. So yeah, short answer is I don't know how seriously memory burden should be taken.
Okay, thanks. So there is another question by Harris. So he is asking that when was the asteroid mass black holes were formed in the early universe?
Oh, yeah, good question. Off the top of my head, I don't have a number, but we can go back to the equation for the horizon mass. So 10 to the 15 is 10 to the minus 23 seconds. So it's just a bit later than 10 to the minus 23 seconds. So it's really very early.
Okay. Thanks. So, uh, I had a question. Uh, you were asking that you are saying that we can have multiple fields and also we can have this non-Gaussian initial fluctuation. So, are they by any chance connected or they are completely independent? We can treat them independently or are they connected?
Right. So the large density perturbations are inevitably non-Gaussian, whatever's producing them, even if it's a single field. But you are right in that with multi-field models, there are then additional complexities. So I think the bottom line is, as far as primordial black holes are concerned, non-Gaussianity is inevitable, but the details of exactly what the shape of the perturbation probability distribution is, that will clearly be model dependent, depending on whether you're single field, multi-field, exactly, what inflation models you're looking at.
Okay. Thanks, Professor Green. Okay, so do you have any more questions? You can please unmute and ask. So if there is no more questions, then we thank Professor Glynn once. Oh, okay. So we have another question. So it is again from Harris. He is asking that if we consider spin of primordial black holes, do the constraints change?
Sorry, again, I didn't catch all the words.
If we consider the spin of the black holes, how does the constraints change?
Okay, spin of the primordial black hole. So yes, evaporation constraints change a bit, obviously, if you change the spin. Not so hugely, they shift around. And in fact, I didn't show a picture of the individual evaporation constraints, but there are a whole bunch of different constraints with sort of slightly different assumptions and modeling. And the spin is sort of comparable to the effective spin is comparable to the other assumptions that go on. Spin's not going to affect microlensing and dynamical constraints. Not sure about accretion ones, but if the evaporation constraints are the one where it's clearly significant.
Okay. So Harris is saying thanks. So okay, so if thanks Professor Green. So if we have no more questions, then we can move to the next talk. Ma'am, can you please share the slides with us by mail? Uh, okay, Chandramouli, are you online?
Hi, sorry, can you hear me?
Yes.
Okay, excellent. Should I don't know,
Yes,
start?
uh, you can share the screen so we can check.
Excellent. Just give me 1 second. Trying to get my okay, good. Excellent. Let me just share screen. Can you see my screen?
Yes, we can see the screen. Okay, so we will come to the next talk of today. So it is by Chandramouli-Choudhury from University of Southampton, UK, and he will be talking about simplicity of cosmological correlators. Chandramouli, you can.
Okay. Okay. So thank you very much for inviting me to give the seminar. So as mentioned, I'll be talking about something called simplicity of in correlators, and I would be very happy if people asked questions in the middle or whatever is preferred. Just feel free to interrupt me and just ask me. So let me just take a minute to acknowledge my collaborators. So almost everything I'm going to say can be found in these set of papers. So it's some work which is done in progress with Arthur Lipstein, Joe Marshall, Jaji May, Ivo Sachs, and Pierre Van Hove. Arthur and Joe are based in Durham. Jaji is now in Amsterdam. Ivo is in LMU, and Pierre is an IPHT. And also towards the end, I'll talk about some work which was also done in collaboration with Pratyusha Radu and Kajal Singh, which I'll mention towards the end. I think they're both based in Southampton, and she's based in Liverpool. Very good. So let me start with the content. So let me just give you a brief motivation of how I got interested in this subject of trying to compute what I call in correlators. So it all starts with how we compute observables in flat space. As you all know, scattering is one of the simplest processes that you can study in QFT and quantum gravity, and it allows you to compute certain observables in flat space. In fact, when we first do QFT, we learn about something called scattering amplitudes, which are directly related to physical observables known as the cross sections, which you can actually go and measure in experiments. And usually the way we are taught how to do it is we first compute the S matrix, and then to compute the cross section, we square the S matrix and then perform some phase space integral. And that typically has a structure like this. And this kind of an object, which are usually observed, are the things which we actually observe, are what are called in correlators, since these are really some expectation values in a given in state. And objects of this kind are also generalizable to curved space. Let's say if you're doing something in de Sitter or ADS, these are the things if you actually wanted to measure, you would end up measuring these. Good. Now, usually this process looks convoluted because you have to first compute a quote-unquote physical object, which is like, the amplitude, and you have to then square it and integrate it. And in order to even compute the amplitude, you would have to sum over what are called Feynman diagrams. And we typically do it in momentum space because we want to make use of all the translational symmetry we have. Now, such a computation, as you know, a Feynman diagram, it takes some simple form like this, where you've got some exchange momentum and the mass of the particle getting exchanged, and you have some coupling constants. Of course, for more complicated theories, this starts looking more complicated. But the basic structure of Feynman diagrams involve what are called off-shell particles, and it often has spurious poles in the intermediate steps, which cancel out once you add everything. But sometimes if you just look at one intermediate step, you might have some pole which you don't like. Now, this kind of a computation, even in flat space, starts becoming very difficult very soon. It's not something you might usually encounter in a quantum field theory course. But let's say if you are taking a QFT2 course and you're asked to compute a 6-gluon scattering in something like Yang-Mills theory, you would have to add many diagrams. In fact, you would have to add diagrams which can look very complicated, let's say, for example, things like this. And in fact, historically, this was a major milestone because in 1985, these two guys, Park and Taylor, they actually set out to do this computation. And they had a paper which was, I'm forgetting the exact number, but it's 10 plus pages, which was basically the whole answer. So the answer was a 10 plus page paper. And in fact, they had this wonderful quote in their paper, which is called this: "We hope to obtain a simple analytic form of the answer, making our result not only an experimentalists, but also a theorist's delight." And within 6 months or so, they were able to guess an answer. And they found that if you add all these 200 diagrams and you choose specific polarization tensors, you end up getting an answer which is just one single term with these funny brackets roughly being square roots of dot products of momentum. And this, I think, was a remarkable milestone, which showed that, even though we are computing something which is not quite the full observable, but something like the scattering amplitude, that can have a very messy structure in the intermediate step. And but then you find some very nice structures arising once you add everything up. You can only imagine how hard this computation would be in curve space. But anyway, although this is sometimes often quoted as one of the standard examples, this was not the first time this happened. Because if you're asking something which has to do with, say, gravitons, in fact, if you're even looking at the 4-point graviton scattering, then DeWitt in 1960s actually did this computation where he showed that the 4-point function also involves summing over 2,000 plus terms, which is much worse than what happened previously. But even then, he found many wonderful cancellations which happened. And there was a very similar quote in his paper from 1960s. But it took around 40 years to find this easier approach. So until then, most people, what they used to do was really enumerate all kinds of Feynman diagrams you could have, add them, obtain an amplitude, then you square it, and then get the cross-section and try to make experimental predictions. But it was not easy to, as you see, even do something like a 4-point function in gravity. And this easier way was actually found after 40 years. It's now called the BCFW recursion. And of course, this sort of kick-started what's called the amplitudes program, where you try to basically simplify computations of observables in space. Good. Now, moving forward, you could ask, like, this sort of historic thing, wonderful thing happened for observables in flat space. Could you ask if there are other observables that for which also some simplicity occurs? And could we try to design it in a way such that these other observables are also useful in curve space? For example, the scattering amplitude by itself is not an object that you can use in something like de Sitter space, but could you use it for some other observable? And then you could ask more structural questions. Could you directly compute this kind of observable without ever going through this long procedure of computing the amplitude and so on? And in fact, one such question is about what's called the in correlator. These are basically the naivest thing that you first study in a quantum mechanics course, which is like an expectation value. And for the purpose of our universe, which is close to an FRW universe, these are what are also called cosmological correlators. And they represent fluctuations, and they're useful for computing fluctuations in the CMB. So hence, these are directly related to measurements. But even if you were not motivated from cosmology, and you were just interested in general properties of such response functions, for example, if you're a person who's doing condensed matter field theory or thermal field theory, you would also be naturally interested in these objects because you would want to understand what's called the Schwinger-Keldysh path integral better. And if you were someone who was doing holography, then you might be interested in a part of this object because these kind of states in which you compute these cosmological correlators are directly related to holographic correlators in ADS-CFT. So there are various reasons why you might be interested in objects which are not quite scattering amplitudes, but are also related to either more physical things or also more theoretical things in other spacetimes. Okay, any questions about this broad introduction? Okay, good. Very good. So let me just state my conventions in a second, just so that we are all on the same page. I'm not going to be having a lot of equations on my pages, but it's, I think, still useful to set conventions. I will mostly tell you a story about de Sitter 4 with a metric of this kind. X's represent the spatial direction, so I'll be working in the Poincaré patch. And this has a square root G factor with a 1 over T power 4. Now, this is often useful because it's also related to the metric in flat space by a simple Weil transformation, which is to say that if you forget about the denominator here, then it's exactly the metric in flat space. And the correlation functions we'll be interested in would be of this kind, where you work with some insertions of operators at t equal to 0. So my time runs from minus infinity to plus infinity. Sorry, minus infinity to t equal to 0. And I'll be interested in correlators at this time slice in some given state. And I will almost completely work in what's called momentum space, where I'm basically defining my momentum by a three-dimensional Fourier transform. So I'm taking a Fourier transform along all these x's. And I'll sometimes loosely use the word energy, and that's going to be defined as the modulus of this thing. Of course, there's no good notion of energy conservation in this iter, but this is what I'll mean when I use the word energy. Very good. Excellent. So let's go back to what we are really interested about. The kind of objects you might be interested in if you are studying CMB fluctuations or something are, in some sense, some fluctuations of either gravitons or scalar fields in some given state. So this is the kind of object you might be interested in. And from your QM 101, you would remember that this object, you can basically insert a complete set of states and write it as the following path integral, where you integrate over some given probability density computed out of a state with some insertions. Now, the state is, of course, not unique. There are some choices one makes. In fact, it's an active research area on finding what is the most general class of states you can make. But for our purpose, we'll choose a state which basically started out as a vacuum state at t goes to minus infinity. And that is to say there are no excitations there. And at t equal to 0, the fields take a particular profile, which is what's being defined by this path integral. So this kind of a path integral usually defines an in-out correlator for you, and that's basically what a state is. And it's this object which are often equivalent to computing correlators in anti-de Sitter space. Very good. Now, we've all done path integrals in our QFT courses. And as you know, this kind of a path integral, you can actually do it in perturbation theory. And what we usually, what we usually do is when we write down this perturbative series expansion, the way this path integral is different from what we usually write down is now I have some special thing about t equal to 0. So of course, I'm asking a question which is not covariant in time. But usually when we do QFT, it's everything runs from minus infinity to plus infinity, but now that doesn't happen. So this is basically the main novelty. And as I'll review in a couple of minutes, instead of working with Feynman diagrams, we'll now have what are called Witten diagrams. You can actually do a correlation function computation using what's called the Schwinger-Keldysh path integral, but I'll not review that, and it's not going to be important for our talk now. Good. Excellent. Now, if that definition of a state was confusing, that exact state that I showed in the previous slide also satisfies the Schrödinger equation, which of course we are all familiar with. For instance, if you were working with a harmonic oscillator, then you know that the ground state of the harmonic oscillator you can obtain from this equation with a Hamiltonian of this kind. And that basically gives you a Gaussian profile. Okay. Turns out that there's a similar version you can write down for, let's say, a scalar field. And all that changes is now you have to integrate over all the oscillator modes, as you would normally have to do even when you're doing canonical quantization, for example. So there, the Hamiltonian now becomes your you have a term which is double derivative in the fields, but that comes from the square of the conjugate momentum, and you've got the other term which is the analog of x square coming from the gradient. And you can solve this functional equation now, and you obtain a functional of this kind. So this kind of an object is known as the wave functional. I'll often abuse terminologies and just call it the wave function. And it is a simple exercise to show that you obtain this from the path integral representation here. But it's the details of how it works is not going to be important. Now, as you might have studied in quantum mechanics 1 or quantum mechanics 2, such kind of an equation also generalizes to the case when you have interacting terms. So you have a free Hamiltonian, and then you have some interaction Hamiltonian, and they basically solve some new Schrodinger equation, which, of course, you know how to solve perturbatively. Often the solution for this equation, if you like, or even the path integral representation that I had, can be expressed in this form, where you have a wave function coefficient like this, which multiplies 2 phi's, and then some coefficient like this, which multiplies 4 phi's. Okay. This is exactly how you would write down a perturbative solution in quantum mechanics, except that now my wave functions are dependent on momentum. These objects have a name. They're called the wave function coefficients. And if you were a person who's doing ADS CFD, then this is exactly the one you compute from the ADS partition function. Sometimes this way of doing things is called old-fashioned perturbation theory, because you're sort of working with objects which are not covariant. And it's also not the most convenient way to compute the S matrix. But these are basically the objects which you would use if you wanted to compute expectation values. Excellent. Any questions or comments till now? I can't see the chat, but if there were questions, I'd be happy to answer. Okay, very good. Sorry, yeah. Now, like we use Feynman diagrams to compute scattering amplitudes, you can also use diagrammatic rules to compute these wave function coefficients. And it's named after the person who I think first started using them. These are called Witten diagrams. And what changes from a conventional Feynman diagram now is that you have to take care of the fact that you're evaluating these wave functions on a given time slice. So normally when you're doing scattering a computation for scattering amplitudes, you're integrating from -infinity to +infinity. But now the time slice t equal to 0 plays a special role. So you would still draw the propagators that you normally draw, except that they can end on a time slice now, that there is a meaning to when a propagator ends on a time slice. Okay, so you have the usual propagators that you would have drawn, but apart from that, you also have these propagators. And these guys are called bulk-to-boundary propagators, and these guys are called bulk-to-bulk propagators. The name is self-explanatory. The bulk-to-boundary connects a point in the bulk of de Sitter to this t equal to 0, which is the boundary of de Sitter. And then this bulk-to-bulk is basically connecting 2 points in the bulk. So if I wanted to compute the 4-point wave function coefficient psi4 in something like phi4 theory, I would draw 4 lines with 4 of these points ending on the time slice, with any point ending representing a psi4. Similarly, in phi cube theory, I would have a similar diagram, but now I can have something which is getting exchanged in the bulk. Okay. So these are not to be thought of as loop diagrams from the point of view of an amplitude, but these just represent that these propagators are now ending on a time slice. Now, one more crucial thing that ends up happening for a scattering amplitude in flat space is you've got momentum and energy conservation along all 4 directions. But right now, since you've explicitly broken time translational invariance, you no longer have energy conservation, but you only have momentum conservation along the spatial directions. Okay, good. Just get some water. Let me just demonstrate how these Witten diagrams look like. So for people who are familiar with the subject, they of course know, but let's say if you've never seen a Witten diagram, then just to give you a flavor of how it looks like, I'll consider a massless field in flat space. And as I had mentioned at some point, you can use a Wild transformation to relate these kind of things to fields in de Sitter. So these are also useful toy examples. Now for massless fields in flat space, the bulk-to-boundary propagator, which is this guy, it really looks like a plane wave. Okay, it's basically this, a plane wave which just carries some energy k. But the bulk-to-bulk propagator has a structure which is very similar to your usual Feynman propagators, which is what you would call as the time-ordered propagator in flat space. But apart from that, it starts feeling the effect of the boundary. Since now you have a boundary, you need to also mention what the what happens because of its presence. And if you want to satisfy the boundary conditions, and in this case, it's basically working with Dirichlet boundary condition like this, you find that the propagator has an extra term of this kind. It's easy to check that if you take this extra term into account, then it does satisfy the Dirichlet boundary condition. But it also ends up spoiling one crucial thing, that it makes this propagator not time translational invariant now. Normally, if you did not have this extra piece, then the propagator would be time translational invariant, but now it's not. And this sort of makes things complicated. Good. So if we look at the simple case of even the 3-point wave function coefficient in phi-cube theory, then you would draw this Witten diagram. You would literally multiply these three bulk to boundary propagators, okay, where these k's are mods of the squares of momentum. This is what I'm calling energy. And apart from this, you'll have your usual factor which conserves your spatial momentum. So you'd have the plane waves along the spatial direction. That story, of course, does not change because we never did anything to the spatial directions. And this, so you now have to do these time and position integrals, with the time integrals ending at t equal to 0, and the position integrals being all over. Now, for this structure, these position integrals would just give you spatial momentum conserving delta functions of this kind. And the time integrals will now give you simple poles. Normally, when you're doing an amplitude computation, you would also integrate time from -infinity to +infinity. And hence, instead of this pole, you would have actually gotten a delta function which conserved energy. But since you're not doing that, you don't have energy conservation anymore. And that's basically the content here, that your time integrals are now getting cut off. And instead of getting energy conserving delta functions, you have poles. And this is going to be the general theme in flat space. So for instance, if you now worked with a more complicated diagram, like something with an exchange, but you are still computing the 4-point function, let's say, then you would attach your bulk to boundary propagators, which basically comes from these legs, along with this bulk to bulk propagator now, which remember had this extra boundary term. Now, this computation is actually fairly straightforward. You can put it in Mathematica or whatever software you like. And you would find that in the intermediate steps, you would have some spurious poles, but they would all cancel out and give you somewhat of a nice structure. In fact, there is a very nice recursive rule that you can write down, which allows you to compute the 4-point function in terms of product of 3-point functions. And more generally, it allows you to write down the wave function at higher points in terms of lower point wave functions. And this is some nice recursive rule which you can explain using integration by parts, something which we all study in high school. And something like this also generalizes to other spinning theories. I'll not go into how you derive this recursive rule, but just the only takeaway points here is the fact that you don't have any energy conservation, and hence you don't have a delta function in energy. And like you have for scattering amplitudes, you have various poles of the amplitude which all have some physical meaning. Even in this case, these poles do have a physical meaning. For instance, you can recover your 4-point scattering amplitude by computing the residue at, let's see, this k1 plus k34 equal to 0. So if you computed the residue at a particular pole, you actually end up getting your usual Mandelstam, like 1 over S in this diagram, for example. And so all these poles also have a physical meaning, which have been explored in many cases. And if you're a person who's working in holography, then you can, in principle, use the knowledge of ADS-CFT to also bootstrap these kind of wave functions sometimes. Good. Now, this was all for a very special case in flat space. Are there any questions about just flat space wave functions? Okay. Now, let me tell you what starts happening when you actually try to compute the observable or the expectation values in something like even flat space and then de Sitter. Now, remember, this was still the wave function that I just showed you. But of course, having the wave function itself is not enough. Like just as having the S matrix itself is not enough, you also need to square it and compute the cross section. You need to do a similar thing here. So once you have the wave function, you can expand this guy perturbatively. So we had the expression for this wave function a few slides ago. And in this step, I'm just doing a perturbative expansion along with the insertions of fields which indicate the endpoint correlator that I want to compute. So for instance, for the 4-point function, this thing would represent the 4-point wave function that I showed you in the previous slide, which was this guy. Plus, just from the next order term here, you would get a contribution also from the lower point wave function coefficients. Okay, so the full correlator, for which you had to do this extra path integral, arises from a sum of two terms, where one term comes from psi4, and the other term comes from the product of the 3-point wave function coefficients. Now, just for this example, you might say, oh, well, what was the big deal? It's just one more term. But let's say you just went to the next higher point, let's say the 5-point function, you would have to take 20 terms like this. And it can soon get very complicated the moment you want to do even at the level of 4-point functions, for example. I'll tell you what the difficulties start showing up. And in fact, it gets worse in de Sitter. So remember that I just told you this in flat space just to keep our life simple and not to scare you away in the first 5 slides. In de Sitter now, you also have to take care of this vertex factor. If you remember in the conventions, I'd already told you there's a vertex factor in de Sitter, which would also now start contributing to the time integrals that you had to do. So let's say you're just computing this 4-point wave function. And if you take this vertex factor into account, you would almost have to do the same integral as before, but now you have this 1 over t1 and 1 over t2. In fact, you can do this time integral for this particular case. And the answer turns out to contain functions what are called polylogarithms. In fact, in this case, it's a dilog. And the dilog is roughly an integral of a log. Okay, so it's some combination like this. But this is sort of strange because this is just a tree-level 4-point function for a very simple theory. And already you start seeing polylogs. So this indicates that some effect like starting to see logarithms and functions beyond that, which for amplitudes typically happens in loops. For de Sitter, it already starts happening for tree-level correlators. Okay, that should already tell you that even tree-level correlators in de Sitter are perhaps as difficult as doing loop-level correlators in amplitudes. Excellent. And of course, this was the wave function. And as I just argued in the previous slide, you have to compute the full correlator. And in this particular case, if you do that, you just end up changing this coefficient from minus pi squared by 6 to pi squared by 3. And like before, you can assign a physical meaning to all of how this structure arises, but I'll not review that now. Good. Now let me just tell you a story about how this field has been evolving and what are the difficulties that people are trying to understand. Now, for this particular example, as I showed, which is just of a scalar field theory, you were able to do the integral, but let's say if you're just asking the question about 5 points, it's not very easy to just do the integral at 5 points, for example. And I think even trying to do these integrals for scalar fields are often difficult. And in general, there are lots of connections which are left to uncover. One such connection here, for example, is this kind of a wave function is you can show that it's exactly related to a particular loop diagram. But in general, there's a lot of structure left to uncover. And if you start asking questions about loops in de Sitter, you can imagine that will be an even harder question. We don't have any explicit example of loops in de Sitter beyond some axisymmetric examples, by which I mean things like bubble diagrams or product of bubbles and so on. For instance, we still don't have a very good understanding of how the triangle diagram looks like, which often you do in a QFT2 course. And in fact, the situation is worse for spinning fields because in this iter, you don't have an MHV-like computation beyond 4 points in Yang-Mills theory. MHV just means that you sum over all channels in Yang-Mills and you substitute some values for the polarization tensors. It's even more ridiculous for the graviton because a priori you have 3 different expressions for the graviton correlator, and it's not obvious to see how these are related to each other. They are just 3 one-page long expressions and sometimes half a page long, but it's not easy to see how you can go from one to the other. And all of these till now have actually been focused on the wave function. But of course, eventually you need to compute the NN correlators, for which you need to do these other path integral that I just described. So as you can imagine, the situation at the moment is still at its infancy, that we have not really understood a lot and there's a lot to do. And I think in this next few slides, I will discuss what I consider a nice step towards trying to directly compute the observable, like the NN correlator, without having to go through all this mess. Something that allows you to use the knowledge of flat space Feynman diagrams and directly compute the NN correlator. Good. Any questions before this thing? Okay. Excellent. So again, to keep things simple, let me just review how the scalars worked and how this computation worked for massless fields in flat space. So if you just evaluated this 4-point function that I wrote down a few slides ago, you have some expression of this kind. I might have used the analytically continued version previously. And if I just substitute the expression for the propagator that I wrote before, except that previously I had written it in a form where I had done this P integral and I had some theta functions, but let's say I didn't do that. This is almost your usual Feynman propagator, but now the fact that you have signs in the numerator just indicate that you have Dirichlet boundary conditions. And the point is, if you try to write the integral in this form and exchange the order of doing the integrals, so let's say I first do the time integrals before the momentum one, then I get an integral representation of this kind, where notice that this very much looks like an integral over the flat space Feynman propagator. So this is almost like a flat space Feynman propagator, and I'm taking this object and I'm attaching some extra integrals on top and integrating it. You could ask if this was a coincidence, and the answer turns out to be yes, that it's only in this case that it happens to be so simple, that even if you wanted to do this at 5 points, for example, it wouldn't be as simple. And in fact, it doesn't work in the same way for loops, or as I said, for higher points. Plus, this was still the wave function. You still need to do more things and compute the correlator. Good. But now if I sort of asked if there was a similar representation for the NN correlator, then turns out the answer is yes. And what you can show is that if you take the full NN correlator, which is obtained by adding these radius pieces, you again get a very similar representation, except that you don't have a p square in this numerator now. So for the wave function, we had an extra p squared, but for the NN correlator, you don't have and end up having that. And here I've also made the connection to the flat space amplitude more explicit because I'm just defining a 4 momentum of this kind. And then in Euclidean flat space, this is precisely my Feynman propagator. But turns out, now this particular kernel is super general. For instance, you could ask what happens with this computation at, let's say, the next order in perturbation theory, which would be like a loop diagram. Turns out you can just use the same kernel and integrate over the flat space loop diagram, like, the bubble diagram. And that's it. That would be the answer for the NN correlator. So this kernel in general is some theory dependent thing, but it generalizes to all points in loops. Good. So what I mean by this is you can take all the diagrams you want in flat space add all the diagrams in your S channel, and simply integrate over this extra momentum piece. Okay. And note that energy conservation exists for these kind of objects. Where energy conservation breaks down is once you have done the P integral. The thing is, as you can imagine, this kernel is channel dependent. So if you're in the S channel, you have some expression. If you're in the T channel, you have to change what you call your 1, 2, 2, 1, 4, and so on. But this kind of a trick generalizes to all points. So for instance, if you were doing the triangle diagram, you would take the loop integral for the triangle diagram in flat space and simply integrate over the energies to obtain the inner correlator. There are some questions about IR divergences that sometimes arise. I can talk about them if there are other questions on that. Anyway, good. So just to summarize, the conclusion is that if you want to obtain an inner correlator in de Sitter, you take your standard Feynman diagram that you would draw, which is, let's say, of this kind, and then you attach two propagators to the end. So in this case, the propagators were super simple. It's just having an expression of this kind. And that's it. That gives you the NN correlators. So you can forget about doing all this wave function, Witten diagrams, and all of the jazz, and simply do this one integral, which uncovers this view. It's an extremely interesting derivation to actually start with that Witten diagram and end up with this. But I'll not have any time to talk about that. But if there are questions, I'm happy to answer. Good. So now just to emphasize how this rule works, you can take the triangle diagram in flat space, which is given by these dark lines. And to each of these vertices, you attach these one-dimensional propagators. And you can also see how this loop integral structure comes up, because now it basically shows how these correlators are somehow a higher loop integral in flat space. Good. Excellent. Although everything that I wrote in the previous slide were for some very simple theories in de Sitter, with, say, what I call conformally coupled scalars. But now a lot of this generalizes to scalars with higher masses. For instance, you can have massless scalars in de Sitter, and then the point is you take the same kind of dressing factor. By dressing factor, I simply mean these kernels, and you just make a shift. You sort of shift this and apply some differential operator, and this gives you the kernels that you need to use for higher masses. Okay, very good. It's something which we also noticed very recently is that a large part of this also works for spinning theories, i.e., you want to compute, let's say, a 4-point Yang-Mills correlator or a 4-point graviton correlator. You simply take your diagrams in flat space and you just attach these extra kernels and integrate over the momentum. And hence, this reduces your computation of trying to do in correlators in de Sitter, if you like, to just computing flat space Feynman diagrams with an extra integral. Good. Now, you could ask, what did this buy you? Like, sure, it might have condensed a lot of things into one term, but does it actually help you do a computation you couldn't have done before? And turns out the answer is yes, but it's a bit of a convoluted way to say yes. For instance, if you're trying to do the bubble diagram, which is the 4-point function in 5-4 theory to order lambda squared, for the in correlator, you actually get this answer. It has a divergent piece, a similar divergent piece like the one you have in flat space, along with some logarithms, very similar logs, like the one you also have in flat space. However, if you try to compute this by the wave function, it's a mess, because the wave function has terms which contain dilogs and log squares. So the in correlator, you can imagine, is a combination of various terms from the wave function coefficient to find this simple structure. But using this integral representation, now it's just a one-shot thing. In fact, it tells you a lot more. This kind of a simplicity, that the in correlator does not have these dilogarithms or log squares and so on, but simply has this logs, actually traces back to a very simple fact about integrals, which is the following. In higher dimension, if you're trying to integrate 1 over L with this measure, then you know that this left-hand side is basically a polynomial. It's a quadratic function of L. Whereas a function like this is a logarithm. And it's differences like this which explain how the simplicity of the in correlator arises. It's something which you can encache and push to higher orders. For instance, for the triangle diagram, you can actually argue the in correlator has to be polylogarithmic, which with a similar leading square root as flat space. Of course, I'm probably rushing over this, but if there are questions, I'm happy to answer. Whereas the wave function is now an elliptic function, and we still do not know an explicit expression for it, but these are more of an argument style things. But anyway, the upshot of this is that this kind of an integral representation now allows you to also do loops in de Sitter. Very good. Since I'm almost out of time, let me also just conclude. The whole point of the story was that I first demonstrated how you have a lot of simplicities that arose in flat space, and it took over 40 years to figure out how those things arose. And in de Sitter, the kind of questions we are even asking now are far more simpler. Like we don't have access to the 6-point graviton scattering or something. But the upshot is that in de Sitter, if you want to compute these in correlators, you can really start thinking about them in terms of flat space Feynman diagrams. And all you have to do is take a Feynman diagram and simply integrate that. And it sort of bypasses the need for computing these wave function coefficients, which can often be long and messy. And it also avoids the computation via Schwinger-Keldysh. It's something I didn't talk about at all, but it's an active approach. Now, something I didn't really emphasize on, but I think it's a very nice fact, is that you can use these kind of correlators to naturally regulate IR divergences in flat space. So hence these correlators end up being natural regulated objects of scattering amplitudes. And now that you have a structure like this, you can start studying what are called cutting rules, which, if you remember from your QFT courses, are related to optical theorems and so on in flat space. And you can write down versions of that in de Sitter. Sometimes you can relate this to what are called the in-out formalism. Again, something I haven't reviewed, but if there are questions, I'm happy to answer. And for future directions, there are, I think, a lot of them, as I had already mentioned before, but just to name a few, you can ask if there's some version of this which fits in with what's called the BCFW recursion in ADS. And if you can find this kind of a structure for more general vacuum states. Until now, for the whole talk, I focused on something called the Bunch-Davies vacuum. But there are more general vacuum states in de Sitter, and you could ask if all of this generalizes there. And finally, which might be of interest to people working in flat space, is there any representation like this for observables in flat space, like the scattering cross-section and so on? And how do you start renormalizing these? So with this, I would like to thank you for your attention.
Thank